Welcome students once again into the class of number theory, and today we will discuss about polynomial congruences. So first of all, what a polynomial congruence is. What a polynomial congruence is. A polynomial congruence is very simply a polynomial congruent to 0 modulo some natural number. For example, if I write 2x cube plus 3x square minus 1 is congruent to 0 modulo 7, then it is a polynomial congruence. In general, you can say that an x raised to the power n plus an minus 1 xn minus 1 plus and so on up to a naught is congruent to 0 modulo m is a general example of a polynomial congruence. So this is what a polynomial congruence is, and now let us discuss about the solution of these polynomial congruences. So I am taking a very general, a very common type of polynomial congruences. So consider this congruence relation, polynomial congruence, you can say 3x power 4 minus 4x cube plus 1 is congruent to 0 modulo 7. So this is a polynomial congruence, and let us now discuss about the solutions of this polynomial congruence. So first of all, look into the CRS modulo this 7. So CRS means complete residue system modulo 7, and what it is, you know it very well that it is the set consisting of 0, 1, 2, 3, 4, 5 and 6. So you have to find solution from this set only. If you are having no solution in this set, that means this polynomial congruence is not solvable. And if some member of this set is a solution of this polynomial congruence, then every natural number congruent to that solution modulo 7 will be a solution. So let us check and then we will discuss in brief. 0. If you substitute 0 here, then 0, 0, 1. 1 congruent to 0 modulo 7 is not true. So that means this 0 is not a solution of this polynomial congruence. Substitute 1 here. So what you will get, 3 into 1 raised to the power 4, that is 3. Minus 4 into 1 is 4 plus 1 is congruent to 0 modulo 7. So it is true because 3 plus 1 is 4, 4 minus 4 is 0, 0 is congruent to 0 modulo 7 is true because 7 divides 0, 0 is a multiple of 7. So this is a solution, but let us discuss rest of the elements also, because the solution of the polynomial congruence is not unique. So let us move ahead with 2. So substitute 2 here. 2 raised to the power 4 is 16 multiplied by 3 is 48 minus 2 cube is 8 multiplied by 4 is 32 plus 1 congruent to 0 modulo 7. Let us see whether it is true or not. So it is 48 minus 32 is 16. 16 plus 1 is 17. 17 congruent to 0 modulo 7 is not true because 7 does not divide 17. So 2 is not a solution. Let us discuss about 3. So what you will get? You will get here 3 power 4. 81 into 3. So 243 minus 3 cube 27 into 4 108 plus 1. So what the result you will get is 135 from here, and 1 is 136. So 136 is congruent to 0 modulo 7. Is it true or not? Yes, it is true because 7 divides this number. Sorry, 7 does not divide 136. So that means 3 is also not a solution. And as we are moving ahead, the numbers are going bigger and bigger. So let us reduce these numbers so that we can easily check whether the congruence relation is true or not. For that, when you will put here 4, so 4 power 4. 4 power 4 you can write 4 square square. So it is 16 square. 16 square into 3 minus 4 into, this is 4 cube. 4 cube is 64 and plus 1. So reduce these numbers modulo 7. Divide the 16 by 7. What the residue you are going to get? 16 divided by 7, the residue will be 2. So replace this 16 by 2 now. So it is 2 here. Similarly, if you divide this 64 by 7, then the residue will be 1. So this 64 can be replaced by 1. And now you are very easy in terms. So this is 12 now minus 4. 12 minus 4 is 8 plus 1. 9 congruent to 0 modulo 7 is again not true. So that means 4 is also not a solution. Let us move ahead to 5. So when you will put 5 here, you will get 3. Once again, 5 square square, so 25 square, minus 4 into this 5 cube is 125 and plus 1 is congruent to 0. Once again, reduce these. So 25 when divided by 7 will give you the residue equal to 4. So replace this 25 by 4. 125 divided by 7 will give you the residue 6. So it is 6 here. And now 4 square, 16 into 3, 48. 48 and minus 24 plus 1 congruent to 0 modulo 7 is once again not true, because you are going to get 25 congruent to 0 and you know that 7 does not divide 25. So this 5 is also not a solution. So this 5 is also not a solution. And let us check now 6. So once again the same thing, reducing the higher numbers. 3 into 36 square minus 4 into 216 plus 1 congruent to 0 modulo 7. And now reduce these. 36 divided by 7 will give you residue equal to 1. 216 divided by 7 will give you the residue 6. And now it is 3 minus 24 plus 1 congruent to 0 modulo 7. So it is 3 plus 1, 4, minus 24 is minus 20. So once again 7 does not divide 20. So the 6 is also not a solution. So you are getting here a unique solution. Always it is not necessary the solution is unique, but here the solution is coming to be unique. And this 1 is a solution means every natural number x congruent to 1 modulo 7 is a solution of this polynomial congruence, that is equation 1. That means if you take your x to be 8, you know that 8 is congruent to 1 modulo 7. It's true, because 7 divides 8 is minus 1. That means 8 is also a solution of this equation. If you take here 15, then 15 is congruent to 1 modulo 7, because 7 divides 15 minus 1, 7 divides 14. So that means 15 is also a solution of this polynomial congruence. So there are infinitely many solutions if you are going to get a single solution from the set of complete residue system. So this is one of the examples, and let us move on to one theorem about polynomial congruences and their solutions. So what the statement is a little bit lengthy. So kindly try to understand the statement first so that you can easily understand the proof of this theorem. So what the theorem says, first I am going to write the statement of the theorem. If degree you can say n, if degree n of fx congruent to 0 modulo p is greater than or equal to p, where p is a prime number, then either every integer is a solution of fx congruent to 0 modulo p, or there exists a monic polynomial. Monic polynomial, you understand what a monic polynomial is? A monic polynomial is a polynomial whose leading coefficient is equal to 1. So either every integer will be a solution, or there exists a monic polynomial gx with integral coefficients such that gx is congruent to 0 modulo p is of degree strictly less than p, and the solutions of gx congruent to 0 modulo p are precisely those of fx congruent to 0 modulo p, where p is a prime number. So very lengthy statement, but it's not difficult to understand. What it says, that you are having this polynomial congruence fx congruent to 0 modulo p, and degree of fx is greater than or equal to p, then one of the two things will happen. Either every integer will be the solution, otherwise there will be a monic polynomial gx such that gx congruent to 0 modulo p, this gx is of degree less than or equal to p, less than p, not less than or equal to, less than p, and the solutions of this polynomial congruence are the same that of fx congruent to 0 modulo p. This what we wanted to prove, and to prove it I'll start with some polynomial fx, and then we will prove that either every integer is a solution, otherwise there is a monic polynomial gx of degree less than p, such that solutions of gx congruent to 0 modulo p and solutions of fx congruent to 0 modulo p are same. So let fx be of degree greater than or equal to p. Divide fx by x power p minus x. The division is possible because degree of fx is greater than or equal to p. That means what I am going to do, I am dividing this fx by x power p minus fx. So definitely by division algorithm you will have some quotient polynomial qx and some residue, or you can say remainder rx, where the remainder rx is either 0 or is a polynomial of degree less than p, because the degree of this x power p minus x is equal to p, so the remainder must be of degree less than p. And if such type of division I am going to do, then this fx can be written as this x power p minus x multiplied by the quotient polynomial qx and plus the remainder polynomial rx, where either your Rx is equal to 0, or degree of Rx is less than P by division algorithm. Now look at this x power P minus x. I am talking about x power P is congruent to x modulo P by formality theorem. You know that it is true. So that means x power P minus x is congruent to 0 modulo P. And if it is congruent to 0 modulo P, then multiplying this by qx will also be congruent to 0 modulo P. And the value of this expression from this equation is fx minus rx. So this means your fx minus rx is congruent to 0 modulo P, or you can say that fx is congruent to rx modulo P. Now two cases arise. Case 1 is that Rx is 0, either Rx is 0 or every coefficient of Rx is divisible by P. Case 1 I am taking, case 1, if Rx is 0 or every coefficient of Rx is divisible by P. In both these cases, your Rx will be congruent to 0 modulo P. It is very clear if Rx is equal to 0, then it is okay. What is the second thing? If every coefficient of Rx is divisible by P. Very simply, if Rx is equal to, you can say, some multiple of P, m1p x raised to the power n plus m2p, some multiple of P, xn minus 1 plus and so on, plus some multiple of P, then you know that multiple of P, when you make it a congruence relation modulo P, then you know that every multiple of P will become 0. So this m1p will become 0. This m2p is a multiple of P will become 0. This mnp is a multiple of P will become 0. So whole of the right side will become 0 and your Rx will be congruent to 0 modulo P, what I have written here. So in this case, your Rx is congruent to 0 modulo P. Now look that fx is congruent to Rx and Rx is congruent to 0 modulo P. By transitivity, fx is congruent to 0 modulo P, and it is true for every x. If it is true for every x belonging to z, that means every integer satisfies this polynomial congruence. So every integer will be a solution of this polynomial congruence. This is the first case when your Rx, your remainder, your residue polynomial is either 0 or each of the coefficient of Rx is divisible by P. Then every integer will become a solution of this polynomial congruence. Fx is congruent to 0. And now we move on to the case 2. Second case is when if at least one coefficient of Rx is not divisible by P. Because in earlier cases we have taken that every coefficient of Rx is divisible by P, and now I am taking the case when at least one of the coefficient of Rx is not divisible by P. Earlier everyone was divisible by P, and now at least one is not divisible by P. So let your Rx be bm x power m plus bm minus 1 x power m minus 1 plus and so on plus b naught. Let this be your Rx. And let bk be the largest, or you can say let k be the largest, not bk. Let k be the largest natural number such that your p does not divide bk. That means p divides bk plus 1, p divides bk plus 2, p divides bk plus 3 and so on, p divides bm. But p does not divide bk. So in that case, keep this in mind that your fx is congruent to Rx modulo p. This we will use it later once again. So here p does not divide bk, and this means since p is a prime number and p does not divide bk, that means GCD of p and bk is 1. And if GCD of p and bk is 1, then there exist integers y and b such that p times y plus b times bk is equal to 1. Because if two natural numbers are co-prime to each other, then at least one of their linear combination is equal to 1. So this is the linear combination of p and bk, which now we are equating to 1. From here, you can say that your bk is congruent to 1 modulo p, because if you are converting an equation into a congruence equation, then congruence is modulo p. Every multiple of p will become 0. So this will become 0 and bk will be congruent to 1 modulo p. Now, what was your Rx? Now move on to the Rx. This is your Rx. And here, if you converting this into modulo p, a is equal to b, so a is congruent to b modulo p. Here bm is there, bm minus 1 is there, but bm is divisible by p, bm minus 1 is divisible by p, and so on to bk plus 1. All the coefficients are divisible by p. So from where we have to start? We will have to start with bk now, because bm will become 0. It is a multiple of p. Because p divides this number. Similarly, pbm minus 1 will become 0. So you will get bk here. You will get bk minus 1 here. And all the coefficients before that, that means bk plus 1, bk plus 2, bk plus 3 and so on, bm, they will become 0 because each one of them is divisible by p and you are having here modulo p. So every multiple of p will become 0. So you are going to get this. And now multiply both sides by b. So what you are going to have, b into rx is b into this. That means the solutions of rx congruent to 0 are same as the solutions of brx, because bbk is congruent to 0, congruent to 1 modulo p. So this bracket, if you will open, what you are going to get bbk, but your bbk is congruent to 1. So you will get xk and rest of the members will be as it is. bk minus 1, xk minus 1 plus and so on b naught modulo p. And rename this polynomial now as gx. I have renamed it as gx. So what is your gx? This is your gx. brx is congruent to gx modulo p, where gx is a monic polynomial. Now the leading coefficient is 1. That means, once again, brx, but your rx was congruent to fx modulo p. So you can replace this rx by fx, because fx and rx, they are congruent to each other modulo p. So rx can be reduced by, can be replaced by fx modulo p. So what you are going to get here now, that bfx is congruent to gx modulo p. That means roots of fx congruent to 0 modulo p and roots of gx congruent to 0 modulo p are same. And that is the second part of the theorem, that either every integer will be solution of fx congruent to 0 modulo p, or there exists a monic polynomial gx such that every solution of gx congruent to 0 modulo p is a solution of fx congruent to 0 modulo p. So this is the proof of the theorem. Next theorem we will take in next lecture, next video lecture. Till then, thank you once again.